Alright, now this is the second part of our video. We're going to go ahead and start from here as we transition into our quantum mechanical model. Now, we know the quantum mechanical model was developed, or at least we usually look at Erwin Schrödinger, but there are actually many scientists who put in information to this model. One of them was Heisenberg, Werner Heisenberg, and we usually study him because we deal with the uncertainty principle. Now, all that the uncertainty principle basically gives us is that we can't know both the speed and velocity, the velocity and position of an electron at any given time. Do not worry, you don't have to go through and calculate this, but you have to at least know the basics of how it works. Looking at, one, the change in position, this dealing with the particle's momentum, and looking at how it's going to work based on Planck's constant divided by 4 times pi, because we are looking at a spherical shape. So your math is going to come in handy a little bit here. Now, when we look at Schrödinger and his input, he basically gave us an equation to explain that an electron functions both as a wave and as a particle. Everything we've dealt with up to this point, we usually deal with it as a particle. We count the charge and we say that it's moving around in space and it can collide and these different things. But one of the things that was shown here is that sometimes it's going to behave a little bit like a wave. And when we look at the structure of the atom and how the electrons are clustered, it's going to give us a better idea of how these interactions between molecules, between atoms sort of work. Now, this wave function is what we call a probability distribution. The intensity of the color used lets us know where the electrons are. The darker the color, that means the higher the probability that we're going to find there. That's what you're seeing here. Whereas the lighter the color, that's where things are a little bit more spread out and you're less likely to find the electrons in those areas. One of the things that we found by using this wave function is the further we go from the nucleus, our probability of finding the electron dips down significantly. It never gets to 0 because they're sort of moving around in that cloud formation. But the further we get out from the nucleus, the less chance that we'll find the electrons in those spaces. Now, when I talked about that whole wave thing, this is how the quantum mechanical model fits in with Bohr. Remember when we talked about Bohr, he had the fact that these electrons travel in this nice little ring. Now, Schrödinger found out that yes, we do have the energy levels, but they don't really follow a circuit. In some ways, they behave more like a wave, and as you're seeing here on our diagram, we're seeing the movement of the waves. This is when the electron is at the 4th energy level. We see the same type of thing when it's reached to the 5th energy level. Look at what happens when we're at 4 1/3. Notice that it doesn't actually match up. It doesn't continue on its path. This is because there's not enough energy to make it to the 5th energy level. This being the case, we never find electrons at this energy level. It's usually at the 4th or at the 5th, nowhere in between. Now, if we look at this in terms of a radial distribution, we have our point where we have 0 in our nucleus. We go up. It's just another way of showing that same graph that we had before. We see a high peak as we get a little bit further from the nucleus. But the further we go, again, we're still dipping down. We're still not dealing with the large number of electrons. The highest concentration is going to be at a certain distance closest to the nucleus. So we're going to continue to look at this a little bit more. Now, the relative orbital size, we can't really define and say it is this exact space or this exact many meters or nanometers. This is why we use the definition that we do to define our atomic radii. Now, the orbital itself is a function or a part of the wave function, and we usually display it in a 3-dimensional electron map. So if we're looking at hydrogen's 1s orbital, we notice that it encompasses or encloses 90% of the electron probability. It's a very, very high chance that you'll find the electron very close to the nucleus for a hydrogen atom, for a 1s orbital. Now, taking a look at this, I know it's very difficult to sort of picture in your mind how an atom looks considering the size. But if you look at the diagram we're seeing here, again, the darker areas, high electron probability. The lighter the areas, we go very, very small percentages away from finding the electrons. Okay? Now, as we continue to look at this, using magnesium as our example, we see that this being our nucleus and our high area of electron density, the entire surface would be 39 cubic angstroms. Now, angstroms is another unit of measurement, very, very small unit of measurements that we use to categorize or to calculate the radius of an atom. Now, based on this information, we can now actually take our time, and we're going to look at how this all plays into our electron configurations. We note here with our electron configuration, and this should be a review from last year, that we start off dealing with the Aufbau Principle. The Aufbau Diagram or Aufbau Principle is just letting us know that our electrons always build from closest to the nucleus, and then they expand and go up to higher levels. So for our oxygen atom, we notice that it starts off in a 1s orbital, the 1 representing the energy level, the S being the type of energy sublevel, and then the 2 letting us know how many electrons are there. Start off at 1s2, then the 2s2, then 2p4 is where we're going to end up, each time increasing in energy as we go. Now, Hund's rule goes a little bit deeper and says that the electron configuration is going to be set up best, or it's going to try to be arranged in a way that takes up the least amount of energy. This ties in with the Pauli exclusion principle, because this means that if we have these electrons that are going into the same p orbital, they're going to try their best to go into each part individually, and I believe this is what we're seeing here. If you're looking at for oxygen, notice we filled our 1s, we filled our 2s, and now we have these 4 electrons that need to go somewhere. The first way that it'll try to fill is each electron will try to get its own space, then from there, then we'll fill it up. Why? It takes more energy to try to force 2 electrons into the same space. Remember, we have that repulsion happening. They're trying to get away from each other. But if we can fill the other areas first, then come back, they're more willing, I guess you'd say, to take on that strain. And don't worry, we're going to talk about it a little bit in class to see if we can't make it a little clearer. Now, when we deal with our valence electrons, we're dealing with those electrons that are usually going to be a part of our s and p orbital. Note that we always said that our valence electrons are going to add up to 8. The highest number that we can have is 8. That's because we're dealing specifically with s and p orbital electrons. 2 that can fit in the s orbital, 6 that can fit in the p orbital. Now, when we deal with our transition metals, you may be saying, okay, so how do we know what it is for them? They still have the same number of electrons, but there's some other things that are coming down the pipe that will sort of allow you to understand that a little bit better. Now, as we look at how the electrons sort of fill, we're going to continue, and how I always say it is we continue down the line until we finish that row. So, with hydrogen, if we're going all the way down to francium, we always begin at our 1s. So we go 1s2, 2s2, 2p6, and so forth down the line. Note that the 3d orbital comes after the 4s orbital. Why? Well, again, everything is done based on energy. It takes a lot less energy for the 4s than it does for the 3d orbital. So, electrons are lazy, they go where there's less energy needed, and we're able to proceed from there. So, our d orbitals will always be 1 row less than our s and p orbitals. Now, this is actually where we're going to end this part of the video, and the next video we're going to do is going to deal specifically with periodic trends. Again, talking a little bit about the patterns that we've already observed and sort of spoken about, but now we're going to try to put a little bit more information with it, see if we can't make it clear. Write down any questions you may have so that we can come into class ready to go tomorrow. Have a great day.